What do Python and Java have in common? In return for a few minutes of your time, I hope to show you why sneaking a peek under the Python hood from time to time can take you to a deeper level of understanding. This is a video all about manipulating functions. We start off with a function definition, nothing out of the ordinary. We're in Jupyter Notebook. Let's call this one Python Bytecode. Let's call our function concatenator. It takes two arguments, a and b, and then it returns the result of a plus b. Because Python is a dynamically typed language, even though we've created this function with the intention of it being called with two strings as arguments, anyone using our function can still pass in any two objects they like. And as long as a plus b is implemented by those types, then it will still work. So, using our function, we've concatenated two strings. But we can also pass in two integers, and it still works, returning 2 plus 3, which is 5. But we want to go deeper, so we start nosying around by seeing what attributes our function object has. So we can see that concatenator itself is a function object. One of its attributes is under code, and this is the code object. So it's here that the compiled bytecode is stored. And look at how many attributes it has. There's the arg count, which is 2, A and B. We've got the file name, flags, which we haven't covered quite yet, and a stack size that we're about to tackle. But my eyes are burning and there's one attribute in particular that we have to take a look at. Code. We're given a bytes object. The documentation tells us that this is supposed to represent the sequence of bytecode instructions. But let's take a closer look. Let's assign this bytes object to the variable unknown bytes. If we make a list of this, then we get this list of 8 integers. We assign this list form to another variable. And when we take a look at the length, we see it's indeed 8. You might be aware of the built-in functions ord and chr character. What ord does is you pass in a string representing a single Unicode character, and then the function ord will return the integer that represents the Unicode code point of that character. So for instance here, we pass in the lowercase p, and we get 112. Chr is the reverse. You pass in a Unicode code point, and then it will return the character that it represents. So we're taking a look at these numbers in our list, 124, 83, and we're not really getting anywhere. It doesn't really make sense. And this is where the Disassembly Module comes in. We import dis, and dis has a function dis. Now what does the dis function do? Well, in its most basic form, you pass in a single argument the object that you want to be disassembled. And it can actually be a whole module that you've written. It can be a class, a method, a function, a generator, or an async generator. Really, you can pass anything into it. The output that you get is text, and it shows you all of the instructions and their order in the bytecode. Now what happens when you run your Python modules is that they're converted to bytecode, and then Python has a virtual machine that runs this bytecode. After the first time of running a module, unless you tell Python otherwise, it will make a folder where your module is, under PyCache, and those files are bytecode, so that the next time that you run your module, the bytecode just needs to be fed into the virtual machine. And so that saves the time spent generating the bytecode in the first place from your code. Of course, what we're covering applies only to the CPython implementation. What we're talking about does not apply to other implementations such as PyPy, Jython, IronPython, and the others. What's more, there are frequently changes between versions of Python, so from Python 3.7 to 3.8, for instance. So we've ascertained that this is 8 bytes in total, but we only have 4 instructions, and when we take a closer look at the numbers, it's interesting to find out that the 124 actually represents the load fast, the first instruction. And then we have another load fast, and so the next number in our list will be 124, as 124 is the number that represents the load fast opcode. Then we have a 23, and that's representing binary add, and 83 return value. But notice, of course, that after each opcode number, there appears to be a 0 or a 1. So what's going on there? Well, if we take the first instruction, load fast, a single byte is the opcode, but load fast has to load a local variable. While that represents the instruction, there's nothing there to indicate which variable needs to be loaded, so we need another byte, and this other byte is used to tell it which local variable to load. In this example, the first load fast says to load local variable 0 and the second loads local variable 1. So they're coming in pairs where the first byte represents the instruction and the second byte is an argument. These load instructions load the values to a shared stack available to be manipulated by further instructions later. If we take a look at binary add, essentially, as it has access to the shared stack, it can just pop the first 2 values from the stack, add them together, and then push the result straight back onto the stack. Remember, stacks have a last in, first out principle, so the last object added will be the first object to come out. The last object pushed will be the first object to be popped. The values running down the left-hand side of the bytecode printout are the offsets where those instructions appear. Naturally, the first instruction starts at 0, index 0. The second instruction is at index 2, because as we just saw, it's 2 bytes large. It has the first byte to indicate which opcode it is, and it has a second byte, which is the argument. While the load fast here is taking up 2 bytes, a few versions ago it took up 3 bytes. But as long as you know the principles that we're going through here, then you'll be comfortable going through code in any version of Python 3. So index 2 and 3 are taken up by load fast, indices 4 and 5 are taken up by binary add, and 6 and 7 are taken up by return value, and that makes a total of 8 bytes. The number in the top left-hand corner, the 2, that represents which line of code this refers to, so it's the origin in the module that you wrote. It's actually much easier to see disassembled code for modules that have more than a single line to be executed. So let's write a different function. This is a basic absolute function that returns the absolute value of the number passed into it. Let's just test our function out briefly to make sure it works. And both 4 and -4 have 4 as their output. Great. We'll delay no more and pass absolute func to be disassembled. You'll notice that there are 3 blocks, so to speak, of instructions in this disassembled output. Each block corresponds to a line originating from the function, and this line number is running down the left-hand side. The first block is line 2, if x greater than 0. The middle block is line 3, return x. And the third and final block is line 5, return -x. To the right of this 5 is the next thing that might jump out from the screen at you, the double greater than symbol. This is to make our lives easier by quickly showing us any jump targets in the disassembled output. But what is a jump target? Other instructions in the instruction set, such as pop jump if false, are able to jump to jump targets and thereby skipping whatever's in between. So the first block represents line 2, which is our if statement. The instructions in order load the value of x, load a constant, 0, CompareOp does a comparison, greater than, and pushes 1, true, to the shared stack if the x value is greater than 0, and 0, false, otherwise. PopJump if false does exactly that. It pops the first value off the stack, and if it's true, it moves on to the next instruction, which is the first instruction of the middle block, representing line 3. If false, then it jumps to the first instruction of the third block, the block representing line 5. That first instruction of the third block is thus a jump target. How does Python know to do the greater than comparison that we want with that CompareOp instruction? Well, there is a for and an enum representing the comparison that we want to perform. For other comparisons, you'll see the CompareOp instruction, but with a different number corresponding to that particular comparison. The only thing left to explain are the bottom 2 instructions. If you look at the instructions from top to bottom, it might seem strange as those final 2 instructions look to be unreachable. They look like dead code. There's a return value in the middle block, which is our return x from the code that we wrote. Then for our return negative x, i.e. the third block of instructions, we have load fast, which loads the local variable x, unary negative, which in our case makes our negative input positive, then return value. So why then do the instructions go on to load the constant none and then return again? That's not possible, it's unreachable. Well, this is indeed dead code. You see, CPython has an easy to understand code generation mechanism. One of the rules is that if a function doesn't end in a return statement itself, there is an implicit load const of none and then return value. This is why all functions defined in Python will return none unless there is an explicit alternative. If you look closely at the function we've written, both of the returns are nested in either an if block or an else block. We haven't actually put an explicit return statement at the top level of the function. And so that's what's going on there. I hope this tutorial gave you a bit of an introduction to understanding Python bytecode and helps you to think a bit more deeply about what's going on when you do write your modules. Take care now.